Section 5. Types of reactions and gas production. Chem Talk. Kinds of chemical reactions. Single replacement reactions. The reaction in this investigation that produces hydrogen gas was a single replacement reaction. In this type of reaction, substances are rearranged and one element takes the place of another in a compound. The result is two new products. The general equation for this type of reaction can be written as follows. The reaction you carried out to produce hydrogen gas was zinc plus hydrochloric acid produces hydrogen plus zinc chloride. You can see how it fits the pattern in the general equation. The zinc replaced the hydrogen. It can be written as a formula equation as follows. Using models, the equation would look like this. Produces. You probably noticed that there is something wrong with the equation in drawing. When writing chemical equations representing reactions, it is important that the numbers of atoms on both sides of the equation are equal because mass cannot be created or destroyed in a chemical reaction. In the above reaction as written, you see that there are two atoms of hydrogen on the right side of the equation, while there is only one on the left. You must adjust the proportions of the reactants and products to satisfy the law of conservation of mass. Remember, in a chemical reaction, atoms are rearranged to form different compounds. When bonds are broken and new bonds are formed, the atoms are not changed or destroyed. They are simply rearranged. Therefore, you must balance the equation. You can do this by placing numeral coefficients in front of the different reactants and products. In this reaction, you could place a 2 in front of the HCl. That would give 2 hydrogen atoms on each side of the equation. There are also equal numbers of atoms of zinc and chlorine on both sides of the equation. The balanced equation is represented as. This tells you that one atom of zinc reacts with 2 molecules of hydrochloric acid to yield 1 molecule of hydrogen gas and 1 unit of zinc chloride. Zinc chloride is an ionic compound, so it cannot be called a molecule. It should be noted that you balance equations only by placing coefficients in front of the reactants and products. You cannot change the subscripts in the molecular formulas. The subscripts cannot change because then you would change the compound you were representing. If there is only one chemical unit in the balanced equation, then you do not write the numeral 1 as a coefficient. The coefficient is understood. Since single molecules are so small, chemists use a larger quantity when referring to chemical reactions. Chemists use moles to represent large quantities of small particles. A mole of molecules, or anything for that matter, is equal to 6.022 times 10 to the 23rd power of these molecules. Since the number of particles in a mole is constant, the ratio in the balanced equation does not change. The equation can now be read as, let me scroll up a little bit so you can see the equation. Okay, here we go. 1 mole of zinc reacts with 2 moles of hydrochloric acid to produce 1 mole of hydrogen gas and 1 mole of zinc chloride. This is a much larger quantity than individual molecules and is one that can be easily measured in the laboratory. You will find out more about this in the next section. Redox reactions. All single replacement reactions are also called redox reactions because they involve both reduction and oxidation. Reaction of a metal with an acid is an example of one atom being oxidized or losing electrons, and an ion being reduced or gaining electrons to become an atom. Decomposition reactions. The reaction in this investigation that produced oxygen gas was a decomposition reaction. In a decomposition reaction, a more complex compound breaks down into simpler substances. The general equation for a decomposition reaction is reactants A and B become separate products. The products of decomposition reactions may be 2 elements, an element and a compound, or 2 compounds. Okay, in this case, it's a compound, and then it decomposes into 2 elements. So it would be this one for that example. In any case, they will be simpler than the reactant. So here's the reactant, and then you have the simpler products. The reaction you used to produce oxygen gas was the decomposition of hydrogen peroxide. It was catalyzed or sped up by adding manganese dioxide. Since the manganese dioxide is a catalyst and not a reactant, it is shown above the arrow in the equation. The word equation is, and the chemical equation is, okay, there's your catalyst. That's why it's up there. That's a catalyst. This equation is not balanced. Placing a 2 in front of H2O changes the odd number of oxygen atoms to an even number. This now gives a total of 4 oxygen atoms in the products. If a 2 is placed in front of the H2O2 on the reactant side, it too will now have 4 oxygen atoms. Checking the number of hydrogen atoms indicates that there are 4 on each side. The equation is now balanced and shows the correct coefficients for the reactants and the products. Okay, let me scroll up because it's referring to this picture. It can now be read as 2 moles of hydrogen peroxide decompose to produce 1 mole of oxygen and 2 moles of water. Okay, so there's the 2 moles of hydrogen peroxide, and then they decompose to produce 1 mole of oxygen and 2 moles of water. Okay, so that's that. Double replacement reactions. Carbon dioxide gas was produced by a double replacement reaction. In a double replacement reaction, parts of 2 compounds in solution switch places with each other. The general equation for a double replacement reaction is reactants AB plus CD, and then these are the products. The word equation for the reaction that you did is hydrochloric acid plus sodium hydroxide carbonate produces sodium chloride plus carbonic acid. The carbonic acid decomposed into water and carbon dioxide, so the entire equation would be hydrochloric acid plus sodium hydrogen carbonate produces sodium chloride plus water plus CO2. Note, if you are talking about the gas, then HCl is called hydrogen chloride, but if the gas is dissolved in water, then HCl is called hydrochloric acid. Okay, let me scroll down a little bit. The chemical equation would be by counting the number of HCl, NaC, and O atoms of the reactants and products, you can see that the equation is balanced. Acid-base reactions. When double replacement reactions involving an acid and a base produce water and a salt, they can also be classified as acid-base reactions. For example, the simple reaction between hydrochloric acid and sodium hydroxide is a double replacement reaction. At the same time, it is an example of an acid-base reaction. Okay, so this is hydrochloric acid. This is sodium hydroxide. So you have hydrochloric acid plus sodium hydroxide produces, sodium chloride and water. Okay, precipitation reactions. Reactions that produce a precipitate, a solid that comes out of a solution, are also double replacement reactions. For example, the reaction when two solutions of salts are mixed, silver nitrate and sodium chloride, yields a solid precipitate. Okay, so silver chloride. The other ions in the solution, sodium and nitrate, remain as a salt solution. Synthesis reactions. In the rocket, a mixture of hydrogen and oxygen was made to react. The reaction was a synthesis reaction, in which two simple substances combine to form a more complex substance. The general equation for a synthesis reaction is an element plus another element reactant equal the product of those two elements. The word equation for the reaction in the rocket is hydrogen plus oxygen produce water. The balanced chemical equation is the ratio of hydrogen to oxygen is 2 moles to 1 mole in the balanced equation. You might have noticed as you were testing your rockets that more hydrogen than oxygen was needed for the rocket to work well. The balanced equation gives you a clue as to why. Okay, so here's the hydrogen, and then here's the oxygen. All right. Analysis of reaction types. Reactions can be categorized as follows. Single replacement reactions, usually redox reactions in which one substance is oxidized and another substance is reduced. Metal-acid reactions are a common example of this. Decomposition reactions. There are only a few examples of these, but they are characterized by a more complex compound breaking down to simpler compounds. Double replacement reactions. This type of reaction is recognizable by two reactants going to two products. The reason they go to products is the formation of water, acid-base, a gas, often carbon dioxide, or a precipitate. Acid-base reactions are common examples. Synthesis reactions. Reactions where two elements react to form a new single compound. Combustion reactions are common examples. Often these also can be redox reactions.